till now we have discussed a question on the two topics, which is a momentum transfer and thermal conductivity. For question number 5, we are going to discuss topic on mass transfer or diffusivity. We will have question number 5. States that diffusion of A through non-diffusing B. 2 millimeter thick layer we have given with 2 mm thick layer. 2 mm thick layer of water on floor of a room. Water vaporizes and diffuses through a stagnant film of air of estimated thickness of, we have got the air thickness as 2.5 mm on the water surface. Under these condition of evaporation, the water temperature is equal to its wet bulb temperature. If ambient temperature is or air temperature is given as 28 degrees Celsius, we calculate the time required for water layer to disappear completely for the following cases. We have got the two cases. The ambient air has relative humidity as 60%, and we have got the floor has micropores and water penetrates the floor at a constant rate of 0.1 kg per meter square. We have got some pressure values so as to calculate it in log form. We have got the diffusivity of water in air as 0.853 feet square per hour. We have to find this condition. Okay, so now let's start. To calculate the pressure, we have to know the Antoine equation. We know the Antoine equation. It states that log 10P A minus B C plus T. We have got the temperature as 301 Kelvin. Just put this temperature in this to get the value of ln P. Substituting the value, we got the value of A, we got the value of C. It is given in the question, just putting T here. We got at PB, we got at 0.03744 bar. We have to calculate the pressure. We know that the temperature was given as 301 Kelvin, but this is dry bulb temperature, and we have got the 60% relative humidity. So we are using the psychometric chart to obtain the wet bulb temperature. We get the value as 22.5 at the wet bulb temperature. We know the water vapor, which is a diffusing, is A, and the air layer, which is B. We are taking the average temperature 28.5, which is dBT, dry bulb temperature 22.5, this is WBT, wet bulb temperature, and 25.2 or 298.2 Kelvin. Diffusivity we are given in water will be, we have to find from this relation. This is the formula. We have to put all the values in this formula. To get the steady state flux of water vapor, we know the value of steady state flux is given by diffusivity, pressure, Rydberg constant, temperature, and the length. This Ln term. Let's draw the diagram of the question to get it more clear. In this we have water layer. This is constant concrete pump. Water layer which is 2 mm thick. Total is 2 time. We have time for complete evaporation. We have kept as 2 kg per meters cube, 3.623 10 to the minus 5 to get the 15.3 R. We have calculated the first part. Now moving to the second part, the combined rate of heat loss. Combined rate of heat loss. Heat loss of water by penetration in floor by vaporization will be given as given as 0.1 kg per meter square hour. This is known as penetration. The water passes through the micropores present on the air, plus we will calculate the diffusivity. This is coming as 0.234 kg per meter square hour. We have to now find the time for disappearance of water, which is this is thickness of water layer upon the mass flux we have calculated. We have got the 8.68 hours time for disappearance of water from the layer of the air, which is 2 mm thick. Okay. Now we will go to the sixth question, which is of equimolar counter diffusion. These questions, first we'll draw the figure. There it is, 80% into 20% O2. This is given as 5 centimeter. This is given as 10 centimeter. 20% N2, 50% O2. This is one. Now we'll first read the question. Two large tanks, this first and this is two large vessels are connected by a tube 5 centimeter in dia and 15 centimeter in length. A vessel 1 contains 80% of N2 and 20% of O2. We will consider this as A and this as B. Vessel 2 contains 20% of N2 and 80% of O2. Temperature is given as 20 degree and total pressure is given as 2 atm. We have to calculate the steady state flux and the rate of transport of N2 from a vessel 1 to vessel 2. The same quantity for O2. The partial pressure of N2 and its gradient in 2, which is given as 0.05 meter from vessel 1. The net flux with respect to stationary observer. The diffusivity of N2 O2 is given as 0.23 centimeters square per second at a temperature of 316 Kelvin. Okay. Now let's start. It is given the diffusivity of N2O2 mixture is 0.023. We will calculate as the respective. This is we are converting the given temperature in Kelvin by adding it 273 upon 316. It is a generalized formula to calculate the diffusivity. It is coming at 1.01 into 10 ki power minus 5 meter per second. We will now then calculate the pressure 1. The pressure at a steady state is given as 2 atm and the concentration of N2 in the first vessel is given as 80%, which is 0.8. The pressure is coming at 1.6 atm. For oxygen, the pressure at steady state is given as 2 atm and the concentration of O2 at vessel 1 is given as 20%, which is 0.2. Therefore, it is coming at 0.4 atm. We have to first find the steady state flux and the rate of evaporation of N2. The steady state flux we will calculate from this. We know the formula, the diffusivity RTL upon PA1 minus PA2. Substitute the value. This value is given in the question. We are taking R as 0.023. To temperature is given 20 degree. In Kelvin it would be 293 into the length between the two tanks, and the pressure we have just calculated 1.6 minus 0.4. It is coming at 3.36 into 10 ki power minus 6 kilomole per meter second square. We have calculated the first part. In first part, it is given the part B. Part B states that the N2 from the vessel 1 to vessel 2 means we have to calculate the N2. How it is the rate of transfer of N2? It is coming as rate of transport. Rate of transport of N2 is coming as 1.963 into 10 k power minus 2, from which it is the area pi by 4 into d square. D square is 5 centimeter. We have converted to meter. From this we have got this. From the rate of transport of N2 means area into diffusivity, which we have just calculated 3.36 into 10 to the power minus 6, which is coming as 6.6 into 10 to the power minus 9 kilomole per second. Since in the question it is given that it is equimolar, for part B we are talking about equimolar counter diffusion. Which means that the rate of transfer of oxygen would be the same as the rate of transfer of a nitrogen, but with a negative sign. We have calculated both the parts, and both parts are remaining. We will calculated the part A and B. Now we are calculate the part C, which is asking us to calculate the partial pressure of N2 and its gradient in tubes, which of 0.05 meter from vessel 1. We know the partial pressure at a distance, which is 0.15 meter, which will be calculated as, from this we know the value of Pa2, which is oxygen in vessel 1, to atm it's at steady state, and 0.2 its concentration, from where we got the 0.1 and 1.6, 2 into concentration of N2, we have got this into L 0.15. From here we will got the value at minus atm per meter. We have to find the value of pressure. We have just calculated 1.6 plus, we have just calculated putting the value above in here. We know the value of the distance between the tube is 0.05, putting here we got the value of pressure, which is equals to 1.2 atm. Part C is also done. Now we are moving it to the last part, last and the most important part, which is net mass transfer. We have to calculate the net mass flux with respect to stationary observer, given the diffusivity of N2O2 0.023 centimeter per second square. We have to calculate the net mass flux. Net mass flux. We know the equation: net mass flux, molecular flux of N2 and the concentration of N2, plus Mb, we are taking that oxygen in tank 1, and Nb. Just calculate where mass of N2 will be 28 minus oxygen will be, mass of oxygen is 32. Taking this side, 28 minus 32 into our diffusivity, and B minus Na is diffusivity, which is we have just it is given, or we have just calculated it 3.36 into 10 to the power minus 6. After calculating, we get the net mass flux would be minus 1.344 into 10 to the power minus 5 kilomole per meter square per second. Thank you.